Students usually first hear about the number I in high school. I is introduced as the square root of -1, and complex numbers are defined to be numbers of the form a plus bi. Following that, students are given rules of complex number arithmetic. They are given some definitions, and then complex numbers are seen frequently in algebra, for example, as the solutions of certain quadratic equations. I am afraid such treatment makes complex numbers seem like an end in themselves and deprives students of an understanding of why they are studying complex numbers in the first place and how legit it is to use these new numbers in solving problems. My idea with this video is to step back a bit. Consider the numbers that you're likely comfortable with, numbers on the number line. If you take any number on the number line and square it, you get a positive number. So, there is no number on the number line that can be square root of a negative number. What then is this definition of I as the square root of -1? It does not help that we call numbers like I or 4i imaginary. If we merely imagine these numbers, how is it okay to just use I in our calculations? Can we rely on the results of such calculations? And what does a number written as 3 plus 4i mean? How do such numbers relate to the numbers on the number line? We'll answer these questions in this video. I'm hoping that the context that we build as we seek answers to these questions convinces us to use complex numbers as freely for solving problems as any other numbers we may have seen before. To answer the questions on complex numbers that we posed earlier, let us look at the number line. On the number line, we have whole numbers, negative integers, rational numbers, which are the familiar fractions, and irrational numbers. We call the collection of all numbers on the number line the set of real numbers. We denote this set by the letter R. Now say we are tasked with inventing a set of numbers that's bigger than the set of real numbers. You might ask, why should we do that? We could presume that the set of real numbers is too small and limiting to solve certain problems, and we need a bigger set of numbers to give us more freedom to make our calculations in such problems. Later in the video, we'll talk about an actual problem where real numbers fall short and where the bigger set of numbers helps us. For now, to get an appreciation for this idea of solving a problem using the extra numbers from a bigger set, let us consider a situation with the set of whole numbers. Recall that whole numbers start from 0 and count up by 1. We denote the set of whole numbers by W. Consider this elementary school problem involving whole numbers. John and his two friends together own a 5-acre lot. Separately, he owns a 7-acre lot together with his two other friends. How much does John own in all? We find the answer by dividing 5 by 3, 7 by 3 and adding the 2 up. John owns 4 acres in all. In this problem, all the numbers given in the statement 5 acres and 7 acres were whole numbers. And the final answer 4 acres was also a nice whole number. But in our attempt to solve the problem, we encountered fractions 5 over 3 and 7 over 3. What kind of numbers are these fractions? These are not whole numbers. These numbers belong to the bigger collection of numbers called rational numbers. We denote the set of rational numbers by the letter Q. So, even though the problem was stated using whole numbers and the final answer was also a whole number, our collection of whole numbers was not sufficient to solve this problem. We had to venture out of the set W into the annular space between W and Q to make our calculations. This freedom to go outside of the smaller set into the bigger set is exactly the point of desiring to have a bigger set of numbers. But is such seamless movement into and within the bigger set correct? For our problem that was stated using only numbers from the set W, can we rely on the calculations made using the extra numbers from the set Q? Yes. This is because the arithmetic defined in Q is consistent with the arithmetic that we know from W. The arithmetic on the set of rational numbers with all the rules of fraction arithmetic agrees with the sense of arithmetic that we know from whole numbers. As a simple example, when we add the whole numbers 2 and 3, or when we add rational numbers 2 over 1 and 3 over 1, using the rules of fraction addition, we get the same results. This arithmetic consistency between the bigger set and the smaller set is a critical requirement. And only because of such consistent arithmetic structure, we can use the extra numbers from the bigger set in our calculations, and we can rely on the results of such calculations. Now that we understand the point of having a bigger set of numbers than a given set, let us return to the set of real numbers, the numbers on the number line, and address the task of expanding this set into a bigger set. How do we define a set bigger than the set of real numbers? If real numbers take up all the number line, where do our extra numbers lie? Naturally, we can expand our collection of numbers from the one-dimensional number line to a two-dimensional coordinate plane. What should we call our bigger set of numbers? Let's call that set the set of planar numbers for the time being. We'll denote our set by the letter P. Just like we associate each point on the number line with a real number, we associate each point on the 2D plane with a planar number. How do we write planar numbers? Since we can identify each point on the plane with its coordinates, we'll use a coordinate pair to write a planar number. For example, the coordinate pair 1, 2 represents a single planar number. If planar numbers are all the points on the two-dimensional plane, the set of real numbers are all confined to just the x-axis. X-axis is a number line and all real numbers lie just there. The entire coordinate plane outside of the x-axis are all the extra numbers that we get with our set expansion. Here is a word about a shortcut notation for writing real numbers in the context of planar numbers. For real numbers, since they lie on x-axis and their y-coordinates are zeros, we can omit showing the y-coordinates altogether and just use the single number notation. For example, if we write negative 1.5, that is same as the planar number notation negative 1.5, 0. This is similar to how the number 3 over 1 in rational number notation is equivalent to the whole number 3. A good point to wonder about at this time is what we mean by a number exactly. We've come to expect a few things from a number, haven't we? For example, if we pick certain numbers from the number line, we're able to order them from the smallest to the greatest. Then, if we pick two numbers from the number line, we're able to do arithmetic on them. Now, how can we think of our 2D points as numbers? Do they also have ordering among them? Can we do arithmetic on them? It turns out that we cannot do ordering of the 2D points, but as we will see shortly, we are able to do arithmetic on them just fine. Let us define the first arithmetic operation of addition. Say we want to add two planar numbers a, b and c, d. A natural way to define the addition is to add the respective coordinates. Is this a good way of defining addition? Recall the purpose of planar numbers is to provide us with a bigger set of numbers than real numbers. And when we had a similar situation between whole numbers and rational numbers, we had to make the arithmetic with rational numbers consistent with the arithmetic of whole numbers. Is the addition rule that we have defined here consistent with what we know from real numbers? What does it mean to be consistent? We'll get only to the essence here, but for more details on how arithmetic can be defined consistently, I encourage you to check out the video by the amazingly passionate James Stanton. And if you like more in-depth, rigorous treatment, to check out this paper. The links to both of which can be found in the description of this video. Briefly, we would like two properties to be satisfied at a minimum. Number 1. When adding two real numbers, say 2 and 3, using the above rule, we should get the same answer as what we know from before. That is, since we know 2 plus 3 to be 5, we should expect 20 plus 30 to equal 50. This is indeed the case with the addition rule above. Number 2. When working with real numbers, the number 0 has a special place with addition. 0 is called the additive identity. That means any number plus 0 is equal to itself. We like to preserve that special place for 0 when working with planar numbers as well. Take any planar number AB. We should expect AB plus 0 to be AB itself. Indeed, by the addition rule, we have that to be true as well. So, we're good with our definition of addition operation. Subtraction can be defined in a similar fashion. Subtract out the respective coordinates. The next operation is multiplication. Say we define multiplication in a similar fashion as addition. That is, multiply the respective coordinates. Is this a good way? Does it satisfy the properties that we want? Number 1. When multiplying two real numbers using the above rule, would we get the same answer as what we know already? Let us try it on 2 and 3. That is, 20 and 30. Indeed, we get what we expect. Number 2. Just like 0 has a special place in addition, 1 has a special place in multiplication. 1 is called the multiplicative identity. So, we expect any planar number AB multiplied by 1, 0 to be AB itself. Let's try that. Unfortunately, we fail here with our multiplication rule. We need an alternate definition for multiplication. As unnatural as it may seem, here is what works for multiplication. What happened here? We multiplied the two x coordinates together and we multiplied the two y coordinates together. These two products with a subtraction between them formed a new x coordinate. Then we multiplied the x coordinate of the first number with the y coordinate of the second number. And we multiplied the y coordinate of the first number with the x coordinate of the second number. These two products with an addition between them formed a new y coordinate. For motivation as to why multiplication is defined this way, please check out the video and the paper that I mentioned before. I encourage you to pause the video here to try out this multiplication rule on some two planar numbers, say 3, 4 and 1, 2. Let's go ahead and do the multiplication. Multiply the two x coordinates and multiply the two y coordinates and subtract the two products to form the new x coordinate. Then multiply the x coordinate of the first number with the y coordinate of the second number and multiply the y coordinate of the first number with the x coordinate of the second number and add the two products to form the new y coordinate. We can quickly verify that this multiplication rule satisfies our two consistency requirements. Number 1. Multiplying two real numbers using the above rule gives us the result that we expect. Number 2. Multiplying any planar number AB with the multiplicative identity 1, 0 gives the planar number itself. That was quite an effort. In any case, we have some basic arithmetic defined on our new set of numbers. This is great. Let us get to the question we wanted to answer in the video. What is I? I is the symbol used for the planar number 0, 1. Is that all? Yes, that is all. Just like we use the symbol 2 to stand for the planar number 2, 0, we use the symbol I to stand for the planar number 0, 1. I is clearly not a real number as it does not lie on the x-axis. It's a number in our expanded set of numbers located 1 unit above the origin. What about the often quoted definition of I as the square root of -1? What is nice about what we have done so far is that we do not have to take square root of -1 as the definition of I. We can prove that square root of -1 actually equals I. To prove this, it suffices to prove I square is equal to -1. Using the planar number 0, 1 for I and our multiplication rule, this follows easily. Voila! What would number a plus bi mean? To find the value of it, we replace each symbol by their planar number equivalent and carry out the arithmetic. We see that the value is ab. This is interesting. If a plus bi is same as ab, then we could use a plus bi as the alternate notation for ab. Wait a minute. We saw this notation a plus bi before. This is the complex number notation. If a complex number a plus bi is equal to the planar number ab, can complex numbers be thought of as just the numbers on the 2D coordinate plane? Indeed, that's actually the definition of complex numbers. We had been talking about complex numbers all along. What we called planar numbers were after all complex numbers. When we see a complex number, say 1 minus 2i, we should just see that as an alternate way of writing the number 1, negative 2. In this video, we expanded the set of real numbers into a bigger set of numbers. This bigger set of numbers was the set of complex numbers. Complex numbers are the numbers on the 2D coordinate plane. And I is a shortcut for the complex number 0, 1. This shortcut symbol enables us to write a complex number ab in the alternate notation a plus bi. I does happen to equal square root of -1, as we proved in this video. But this fact, I is equal to square root of -1, is incidental. We cannot take this fact as a starting point for talking about complex numbers, as that would not give us an appreciation for the structure, power, and purpose of complex numbers. The power and purpose of complex numbers are best understood when complex numbers are viewed as the numbers on the 2D plane, obtained by expanding the set of real numbers. We said earlier that there were calculations while solving certain problems where real numbers fall short and where the extra numbers from the bigger set would come to the rescue. What is such a calculation? Taking square root of a negative number. We just mentioned I is equal to square root of -1. This means complex numbers allow us to take square roots of negative numbers, which is impossible if we are sticking to real numbers. And what is a problem that requires us to take square roots of negative numbers? Solving a cubic, where we need to find the x-intercepts of the cubic. Notice that this problem of solving the cubic is stated completely using real numbers, and the final answers, the values of the x-intercepts, are also real numbers. But in the process of finding the answers, we encounter square roots of negative numbers, which means we need to move into the realm of complex numbers to solve this problem. We defer the exact details of solving a cubic to a future video. We believe that the view of complex numbers presented in this video as naturally extending the set of real numbers makes them feel less elusive, less imaginary, and helps to remove hesitation in using them. Thank you for watching.